Here we are with the Chapter 2, Section 1, Day 2 notes. Our objective is to calculate linear regression, so you are going to want to either access the online calculator or get your actual handheld calculator out to be able to calculate that, and use vertical freefall function. Woohoo! Alright, so first thing we're doing here is needing to remember what a linear equation is. So here we are with our linear equation. Technically when we do it, you usually see it as y equals mx plus b, but here they are changing our m to a and b to ob. So there you go. The correlation coefficient that comes up is known as r, and it's a number that measures the strength and direction of the linear correlation of a data set. So a lot of times when I think of R, I think of slope, okay? So I'm going to write feels like slope. Because what happens is if you have a positive correlation coefficient, you actually have a positive slope, all right? And if you have a negative correlation, you have a negative slope. So again, positive and negative slopes in this one. And then when we look at the actual number itself, that's where it's not slope anymore. That's where it's talking about, is it going to be strong or not? So the closer to 1, the stronger it is. And when r is basically 0, it's weak, okay, because clearly that's not close to 1 at all. Now the problem with it being close to 1 is that it also could be -1, okay, and -1 is also assumed to be very nice as well. Just anything that's not close to 0 is what we're looking for. I just can't fit that. There we go. All right. So looking at our next piece here, we've got our correlation. So the idea is that you're looking to see if you can make a line that seems to follow the data. So for instance, down here, don't know why I'm skipping to this one, but you can definitely see that it's going up and to the right, okay? And so we would say that that has a positive correlation and that it has a relatively weak correlation. Because you'll notice that as you circle this entire thing, it's not as nice as, say, this one. Oops, that was a bad line. All right, and so this one's still positive correlation, but this one's a little bit stronger. Because as you look at it, your oval, if you will, that's surrounding each of these, or at least as you're looking at the line, there's a lot more points that would be able to be close to that line or on that line than the other option. This one is going to be as 0 as possible, or as weak as we can see, and so you just kind of get random. It's very hard to even tell if it's trying to go up or down or where the trend is going. So in that case, because you can't even see if it's positive or negative, that's definitely weak. This one over here, we have a negative correlation, again just because the slope is negative, and then we would call that one weak. And then over here, we have a negative correlation again, but then we would call this one strong. Alright, so of course strong correlation is going to be closer to 1, so maybe you'd say that this one is -0.8 as your R. Again, your calculator will actually be able to calculate that, so we're not necessarily going to be just guessing what a correlation number is. We'll actually find it. So the table below shows the number of boxes of cereal sold at a number of different price points. Woohoo! We're going to use our calculator to create a scatter plot and find a line of fit for the data. Now, it turns out it doesn't actually help if you create the scatter plot or not, so if you would like to make your calculator plot dots on it, cool, okay? But it doesn't actually help us when all we really need to do is find the line of fit and then the correlation. So, you can, in fact, on your calculator, go to stat plot and set up the plot, set up the graphing window so that you actually have your x's and your y's within the vision of that. And then you would go ahead and do this part. So this is the part that actually calculates the equation that you're going to need. Alright, this part up here is just the part that does your scatter plot. And again, the scatter plot part is take it or leave it. Because it's just going to be a bunch of random dots on a screen that's not really going to be very easy to read. So, either way, you'll notice that underneath here it also says this word diagnostics. If you don't have your diagnostics on, you will not be able to get an R value. So, you need these on. To get your R value, or your correlation coefficient. Let's see if the next... I think the next bit of slide tells you how to turn that on, but it looks like no. So, in that case, we will go over how to turn on your diagnostics. Super easy. All you need to do for diagnostics... Whoops. So if you're using the online calculator or something other than a TI-83, you can actually just go to Mode and scroll down a bunch until you get to Diagnostics On. You know something's on in your mode if it's highlighted in that dark box, okay? Or you can always, no matter which one you have, go to Second 0, which is your catalog, and scroll down to Diagnostics. Alright, so we scroll all the way down. You can skip technically to the D's, but hey, you may as well just hold down the down arrow. And then you'll get the Diagnostic On and Diagnostic Off option, but of course we want the On. You'd press Enter, and then you have to press Enter again so that it says Done. And that means they're on. If you have your own handheld calculator, they will be on until somehow you accidentally turn them off, which really doesn't happen. So once you do this one time, you're good. Otherwise, again, this is that process. So the problem with the online calculator is that it resets every time, so you do have to turn it on every time. But, I mean, you clearly get used to it, especially because you can just, on the online calculator, go to the mode option and just scroll down to diagnostics. So yay for later versions of the calculator. Alright, so next thing is answering some of our questions. So we're going to describe the correlation of the data. So what we're going to do over here is actually enter the prices into list 1 and list 2. So this one right here is going to be list 1, and this one right here is going to be list 2. So how do you get to your list 1 and list 2? You need to go to Stat, the Stat button, and then you need to select Edit, and then you will be at your lists. So you can, of course, delete each point in there, I guess, or you can actually press Clear and then down. But anyway, so getting to our data, we're going to enter each of these into the list 1 and each of these into the list 2. Alright, so I paused the video to enter all that data in. So again, under your Stat, we're going to describe the correlation of the data. So how do we get that once we enter the data in? Remember, this is your Stat Calc Lin Reg, and then you actually press Enter a few times. So I'm doing this piece here, so I go to my home screen, which is where you do all the little bits of math, press Stat, over to Calc, and then Lin Reg, and then you press Enter. Alright, a bunch of times. So, taking a look, it says the correlation coefficient, just R, not R squared, is negative 0.9805, lots of numbers, okay? So if we want to describe that correlation, that means that it is a strong negative correlation. Okay, so again, you can see there's a negative, so that's where I'm getting negative from it. So if I look at it, the data is going to be going from left to right down. And then it's 0.98, so remember that's very close to a 1, and so in that case, that's why it's strong. So then it asks, what is the slope of the line of best fit? And what does the slope mean in this context? So taking a look at what your calculator is telling you, it tells you that you have y equals ax plus b, and a is negative 15358.9, bunch of numbers after it. So this is actually the slope, because remember that in what we've been looking at, you'd have mx plus b, so slope is your a. And notice that it's negative, which we already said it was going to be because of the correlation. And so we need to know, what does this slope mean in the context of the problem? So when we look at the numbers that we're going for here, this is actually boxes sold going down as price increases. So the price per box increases, and then the number of boxes sold decreases, which makes sense because if it's a more expensive product, you would think you would probably sell less of them. So officially what that means is for every $1 increase, the number of boxes sold decreases by 15359-ish boxes. Okay, and how do I know that? Because again, slope is really just a fraction. So it's technically 15359 over 1, meaning boxes decreased as dollars increase. So that's our fraction. So that's where I'm getting this description. For every $1 here increase, the number of boxes sold decreases by that ridiculous slope number. All right. Then it says, using the line of best fit, how many boxes of cereal would you expect to sell if the price was $2? So we don't have a $2 in our table, so we can't necessarily use that, but I would expect, based on what I can see, that it's going to be more than 38,000 because it's going to be an increase, a decrease of that price. So how do we figure that out? Well, we take our equation, which the calculator has given you to be negative 1535893.93. And that's going to be multiplied by your x, and then to that we'll add the b value, which is 73622.5. But then for this problem itself, we're going to put in, for the x, a 2. So if we plug in an x of 2, that just means 2 times 15358.93 plus 73622.5. So that means that if we have $2 for our price, we're expecting 104,340.36 boxes. And again, all I did was plug in a 2 to that equation. What if the price was $4? So now I'm just going to plug in a 4 for my x. So 4 times, let's see if I can get my entry back. Yes. 4 times 15,358.93, and then plus 73622.5. And so now we're going to get that there are, if it's $4, we're going to have 135,058.22 boxes. All right. Are those numbers actual values or estimates? Oh, I didn't put a negative in there. That is why those numbers are so different. Okay. Let's try that again. 2 times negative 15,358.93. 73622.5. So let's remember our negatives. So that means that we're actually going to have, for 2, 42904.64 boxes. And then for our second one, plugging in a dollar value of 4 plus 73622.5. That's what you get for forgetting a decimal. So 12186.78. Okie dokie. Anyway, so taking a look at number 5, are these numbers actual values or estimates? And this would be estimates. Now, we can say with what feels like a 98% certainty when it comes to looking at the R value there, we see that it's 98. That's kind of how I think of it, as a percent. And so I'm saying, well, it's really close to actually being it, but not exact. Because we cannot, for instance, figure out when COVID's going to happen, and therefore no one's buying whatever these boxes are. So, again, it's never going to be exact, but it is supposed to, based on previous data, be a very good relationship to what you would expect. Alright. So, again, just another list of how to find regression on your calculator. You enter the data by pressing Stat and then entering the data into your Y1 and X1. Again, this guy right here is extra. This is just so that you can view it at some point, but you don't necessarily need to see the dots and then the line going through them to know how related it is, especially if you understand that R value. So then the next piece says, okay, well now you can calculate the regression once your data is in there by doing your stat and then going over to calc and then going down to calc. You don't actually need to do this part here because it will automatically use your L1 and L2. So unless you put them in a completely different list, like you put them into list 3 for some reason, because maybe your list 2 doesn't exist, then you would need to do this thing where we have this L1, L2 thing. But unless your calculator is kind of messed up, you don't really need that. And then the Y1 at the end tells the calculator to store the equation. So if you want to, you can store the equation, but also, again, your equation is given to you. See, they give you that's the format, and then they give you A and B. So you can just plug it in. You don't really need to have it already in the Y equals. So, let's see. Oh, do I have this here? This here is what I've been using on the previous notes. So if you're wondering how I'm getting all these local maximums and minimums when it comes to points of importance, all I do is enter the equation in. Usually my window is actually negative 10 to 10 by 1s and negative 10 to 10 by 1s. Either way, so that I kind of have that central graph. And then if you go to calculate, you can calculate a 0, which means that's these guys here where it intersects the axis. Or your maximum, which of course would be here. If you try to do a minimum for this one, it's not going to be good. So don't do that because there isn't a minimum. And then if you have another equation going through there for some reason, you can find an intersect point. So that would be that one there. So that's how we find maxes and minimums. And if we go to the next page, this is kind of telling you about that whole left bound, right bound thing so that you can understand visually what it's trying to do. So the last piece that we're going to go over is modeling vertical freefall motion. So this is a standard equation that has to do with feet per second, or they say per second squared, when it comes to the pull of gravity. So negative 16 feet per second is actually the gravitational pull of the Earth. So this is a constant that's in here. It will never change. T is going to be your time. So when we're talking about anything moving, like a ball or a rocket or whatever, you do need to have time from when you launched it or when it was thrown to time when it maybe lands. So t is time. Usually it's going to be in whatever, it doesn't matter as long as you keep the same unit throughout. So if for some reason the problem gives you feet per second and then asks you how many miles or something, you'll have to convert, but we don't have those types of problems. So as long as you're putting in seconds, you're going to get seconds out. If you put in minutes, you're going to get minutes out. It's whatever you use, it will come out that way. So you'd have to change it if you didn't want it. Then we have here your initial velocity, and so that's like when it was thrown or launched or dropped sometimes actually, and so they're asking what is the speed. If it's dropped, that's actually 0, all right? So that's nice to know. And then your height, sometimes it'll be on the top of a cliff or a playground or whatever's happening, and so your height is going to be whatever that starting distance is. If you're ever talking about something being thrown or launched height is going to be 0 feet or meters or whatever the problem is asking. Even though technically you're probably about 4 or so feet above the ground because that's how you throw something. You don't just like throw it laying on the ground. But for these references, we are just going to talk about the height being 0 if you're throwing it or launching it. So, unless otherwise specified, which it usually is not. So, here we are. Teddy Bridgewater throws a football straight up in the air. So here we are with one that's saying that, oh, guess what? When he throws it, it's from a height of 5 feet. Again, as I just mentioned, that's because, Teddy Bridgewater is tall and not lying on the ground throwing this ball. And so we're going to say that his arm, or whenever it is released, is 5 feet above the ground. So we're going to write an equation to model this situation. And we are going to use our standard equation here with h of t, which just means the height after time, whatever that time happens to be. And it's going to be negative 16t squared plus the velocity times t, and then plus the height. And so we do know that the height is 5 from what we just read there. And the ball is thrown with an initial velocity of 76 feet per second. So here we are with 76. Notice that it says feet, and we already are using feet, so we do know that that's uniform, which is nice. And so when we do our time, we are going to have seconds. So t is going to be in seconds, because that's what was input in the equation. So first we need to know what is the maximum height of the ball. And so when we think of calculating a maximum, all you're going to do is type this into your calculator and find the maximum under second and the trace key. Okay, so I'm going to take the time to type in this equation. Alright, and make sure that when you're typing this in that you're using the negative sign and not the subtraction, because that's going to change that up and tell you there's a domain error. This is a very ugly looking graph. If you actually graph it on a standard grid, you'll see this and this. Okay, so it turns out the maximum is, somewhere up here, alright? And so you can zoom out if you would like by changing your window, definitely by changing the Y maximum to at least, let's see, 16, I don't know, I'm going to try 20. Let's see what happens. Yep, still not even there. So I don't actually need to see the maximum in order to calculate it. So what I'm going to do is go to second calc and do my maximum. And all I need to do is make sure that I pick something that's around an x of 0, right? Because that would be to the left of wherever this maximum is. And then when I go right bound, I just want to make sure that I pick something, again, that's very close to the cursor being at 0. So according to what I have here, my x needs to be, I'm just scrolling over, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah, this is at about 5. So anything that's around 5, and of course it might not actually show up on your screen. Ooh, mine does at 4.89. Okay, so I did x equals 4.89-ish. And then they want you to guess, so just scroll to the middle somewhere and press enter. And so now I know that the maximum height of this ball is going to be an x value, but that's time, of 2.375, but a y value of 95.25, and so that's the maximum height. How long will it take for the ball to hit the ground? Okay, so that's not how long will it take to get to this height, because that's 2.3 seconds. But it turns out that we can also figure that out by multiplying that time to reach the middle by 2, or we can actually find what we call the zero, as I was saying earlier. So we can do calculate, or second calculate, and then do 0. And then it's going to ask you what's left of that 5-ish number, and then right of that 5-ish number, and then a guess. And so if we calculate this 0, you're going to have an x of 4.8149, and then a y of, at least mine says, 1e negative 11, which literally means 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. So basically 0. Okay, so if you see any e's on there, it just means that it's scientific notation. So 1 times 10 to the negative 11 in this case. So that means that it's going to be at 4.8149 seconds. Or again, if we take a look back at the previous problem, we could have just taken 2.375 and multiplied by 2. And we would have gotten pretty close to the end, because it makes sense that in the middle of this trip, that would be halfway for the time. All right. So that's the idea of your motion equation, and then of course we have the assignment. So that will be tomorrow. Of course you can get started on it today, but